this paper? So this paper is written by a team of people from Stanford at the time. So Richard Chaucher is now with Salesforce. I think Milind Ganju is still studying in Stanford. Everybody in NLP would know Chris Manning, who is with the NLP lab in Stanford, and Andrew Nang of Deep AI. Okay, so this paper has, I think, by this time, more than 1,400 citations this is published in NeurNIPS, first presented in the conference called Neural Information Processing, which is a top-level conference on neural networks. Okay. And after almost 10 years, it has gotten more than 1,400 citations. That's how much this paper is important in the area of NLP, I think also on images and in AI. Okay, so may I just know for you, what is this paper about? So let's keep our answers to 10 words. So for you, what was this paper about? So after reading it, what was the paper talking about? You can place your answers on Mentimeter. Or did you not read the paper? Okay, so transfer learning between images and text, that's right. Zero-shot learning, about a zero-shot model that can differentiate both seen and unseen classes, that's right. So it's about labeling the unlabeled pictures using zero-shot algorithm, understanding categories or words that are new and familiar. So I'll just try to capture some of the words or key terms that are from your answer. So first is zero-shot learning. That's correct. So from the title of the paper, zero-shot learning. So that is a key term. Zero-shot learning is actually is a kind of transfer learning. So where a model learns from previous learnings. Okay, so transfer learning is like the super class. A kind of transfer learning is zero-shot learning. Okay, and then you're using also seen and unseen classes. That is right. So during training, certain categories or classes are seen, but at testing, it is given samples of categories or classes that it did not see during training, and that is zero-shot learning. Okay, and then there's also the algorithm that is able to identify images without being trained using images with text, I guess. So yes, what the paper is talking about is a way to classify images that has not been seen during training from information that it learned from other categories. Okay? So it's zero-shot learning that integrates modalities between image and text. So that this answer captured the second keyword, and that is multimodal data. So in their approach, they did not just use one type of data in zero-shot learning, but it integrated semantic representations from both image and text. That's why it is multimodal. Okay? Okay, so I guess it's from this one. Okay, thank you for your answer. So let's start with, so there are actually three main keywords or key terms that are key concepts in the solution proposed by Socher and the team. So that is, you've got that, zero-shot learning, that's one. And then second would be multimodal, okay, that's two. And the third one, which they did not write in the in the title, but it is part of the seen and unseen. The third concept is novelty detection. So in novelty detection, it is able to identify or to determine if an input to a model is able to identify or determine if a certain input was not part of the training data. Okay, so that is, it's unseen. It knows that if it knows that a certain image, okay, it knows that a certain image was never seen during training, or that category of images was not seen in the training. Okay, so let's go through those three: zero-shot learning, multimodal data, and novelty detection, one by one. Okay, so let's start with zero-shot learning. Okay, so zero-shot learning refers to the ability to perform a task without having received any training samples. So in the case of this paper, this task that they are performing is classification. They are classifying images, and these images are images of animals. Okay, so for this paper, the model is trained on 8 types or 8 classes of animals, and there are 2 classes of animals that it has never seen, but the model is able to identify them. Okay, so basically, if we are going to use the cheetah, the leopard, and the jaguar as example for zero-shot learning, during training, the model is the model saw that the cheetah has these samples of cheetahs at different angles and samples of leopard at different angles. But at testing time, the model may be given images of cheetahs and leopards, but aside from that, it would also be given an image of a jaguar. And through zero-shot learning, it should be able to identify that this image is of a jaguar based on what it has learned or based on the features that it has seen from the cheetah and the leopard. So there are similarities among these 3 types of cat animals. So basically, they only differ a bit on the weight and maybe on the patterns on their fur or hair. So using zero-shot learning, the model is expected to be able to classify a certain image of this animal as a jaguar, even if it did not see a jaguar during training. That is zero-shot learning. Okay? So when zero-shot learning was introduced, both for NLP and for images, it is a welcome solution because it's very useful. In reality, we cannot really have a training set that would be complete and comprehensive enough to have all categories covered. It's impossible also for the one creating the training set to anticipate all possible classes. So let's say we want to classify or come up with a model that could identify the kind of animal, but there are so many animals in the world, right? So how can we come up with a complete data set? So if we're coming up with a classifier for, let's say, products, there would always be new models of different products. So the training set would never be complete. So it's hope with zero-shot learning. So even if our data would eventually contain new data items, we are hoping that it would be able to still identify those categories and those inputs from the features that were extracted during the training part. Okay, so for this paper, what they did was the model was exposed or saw 8 types of animals, and then at testing, that model was given images of 10 types of animals, and they want to see what the accuracy is and how good was the model in identifying the 2 unseen categories. Okay, so that is zero-shot learning. Are there questions on this one? So that's zero-shot learning. The second key concept in that paper is multimodal embedding. So we go first to what an embedding is. So embeddings are numerical representations of data such that those vector or array of numbers is able to capture information about that data. So we have In NLP, we have word embeddings. So words are represented as an array of numbers, depending on how many, it is up to the one who's designing the embeddings to indicate how many numbers or dimensions are in that word vector. Okay, in images, they also have image embeddings. So instead of keeping the image itself, an image is represented by an array of numbers again, and that is the vector, a vector of numbers. And those numbers would describe and represent that image. Once data is represented as a vector of numbers, it's now easy to project it onto a plane like this one, onto a space. So in the case of this paper, they use two modes of data. Okay, the data that they used are images, okay, and text. So that's why it's multimodal. They use both word embeddings and also image embeddings. Okay, this is actually a projection, a Disney visualization of the semantic word space. So they got a corpora of a text corpora and then generated the semantic word space. So all the words in that corpora were represented as embeddings, and then once embeddings are there, they projected it using Disney. This is the Disney visualization. So the word vectors are actually highlighted. So these symbols, they would represent, so let's say the ship. Let me use a better one. So let's say the triangle, they represent birds. So this part, they are all triangles. So this is the space where the bird or for different forms of birds as words. So maybe they are doves, I don't know, myna bird, parrots, etc., they appear here. Now, just those colors alone, okay, without the words. So without the words, just the colors alone and the symbols, they represent the word semantic space. They are from the word embeddings. Then what the team did was, based on the word embeddings, okay, given the eight, these are the categories, the image categories. Actually, it's 10. There's 8 that is seen and 2 that are unseen. So they have 10 categories of the images. They mapped an image embedding. So let's say the cat, when it is mapped to the word space embedding, so to the word semantic space, it is somewhere here. As you would notice, the cat is here because the cat is unseen. The model or the embedding the image embeddings never did not cover the cat image. It is the unseen category. The second unseen image is the truck. So the truck, since it was never seen, it is somewhere here. Then for the seen category, so that's the frog, the bird, the deer, etc., they map the image embedding to the word embedding. So this is the image embedding for a frog, and the frog is somewhere here for the word embeddings. So which is why this visualization is a mapping of the text or the word semantic space mapped to the image embedding of the known and unknown categories. Now we have a multimodal embedding. Okay, so this embedding that they're using relate information from two sources. So the two sources are a text corpora and an image corpora. Okay, and from here, it can now represent, this space now represents not just words and their meanings, but how those words relate to the image. Okay, so this is the second concept used in this paper. Okay, the last one is the identification of novel or unusual data from within a data set. Okay, so these outliers or anomalies are discovered due to their differences from the rest of the data that has already been seen. So another way to say it would be novelty detection works by identifying the outlying data. So these are the data that it has seen. So in novelty detection, it is looking for the outliers or novel data, data that it has not seen. Okay, so these are the outlying data and information. And to properly classify these outlying data, a machine learning algorithm may be trained only on the correct data. So let's say this is one model, okay, and this model can detect one class. So this, let's call it the normal class. So in novelty detection, by knowing this class, hopefully it would be able to identify data that is not part of that normal class. So this is novelty detection. In multi-class novelty detection, the model knows n number of classes, and then given some input, it can identify, a novelty detector model can identify whether something belongs to a class or it is an outlier. It is a novelty. So it can identify seen, these are the seen categories, and unseen categories. So that is the third concept used in that paper. So what the work of Socher did was to combine those three. So it did zero-shot learning, so it can identify or classify new images, even if it did not see it before, okay? And to do that, it used multimodal embeddings, meaning it used information from text and then matched it with the information from the image that it saw before, okay? And then using novelty detection, it identifies if a new image hasn't been seen before and somehow identifies the class, using the class of these unseen images based on the multimodal embedding that it has created. Okay? That's what their work is about. At the time, these three, they're not new. People were already doing zero-shot learning for both words and images. There's already multimodal embeddings. Actually, it was Socher who introduced it, if I'm not mistaken. And then novelty detection is already being done in images. But what this team did was to combine all three to come up with a zero-shot novelty detector using multimodal embeddings. Okay? So in your own word, so what is this paper about? So this paper, so let me just break it down further. So in this paper, based on a combination of word and image embeddings, okay, and novelty detection. So this work provides a model that can categorize images with classes for which there was no example in the training set. Okay? And then how are they able to identify the unseen classes? They did that using distance computation. So using distances in the multimodal embedding space between the test image and the unseen and seen class labels, their technique can provide a probability of a new image belonging to a class that it has never seen before. So what does it mean? So let's say it sees a certain image. So it sees a certain image, and that image, the representation of that image falls somewhere here in the, it's embedding, that image embedding falls somewhere here. Since it doesn't fall in any of the word semantic space, it computes to the nearest image, unseen image class that it can find in multimodal embedding. So let's say from an image, given an input, that input image was converted into a feature vector. That feature vector would be mapped here, and then depending on where it falls in the feature space, it would know if it's seen it or not. So if it falls within this space, then it's seen it, and then it will just perform some classification, maybe via softmax. But if it is an outlier, an image embedding falls outside the embedding space, so it's an outlier, it would simply use the distance computation to know which of the unseen classes that image belongs to. Okay, so that's what it does. And then finally, these are utilized to determine, in their study, they determined which classifier to employ. So should they just use the novelty detector, or if something is unseen, or should they use a traditional softmax classifier or any other classifier, whether it's a machine learning or deep learning classifier, to identify from the 8 known categories for an unseen or for a seen category. Okay, are there questions from this point? Okay, so if there are none, so just to explain further the process. So there are 3 things when we do or when we create any AI model. So there must be that model would have some knowledge. Normally we get it during training, and there is a process that's being done and what the results are. So this is what they did. So for their knowledge, their training data are images with labels, and they know 8 labels. And then aside from the training data, they also have the multimodal embedding. So they use both word embeddings from a large text corpora and image embeddings from the training data. And then the images were mapped. What did they do? First thing they did was the image labels, or the image labels and embeddings were mapped to the word embeddings. Okay, and then the image embeddings determine whether an image is of a seen or unseen class. So novelty, it's the novelty detection algorithm that differentiates whether an image input has been seen or unseen. Okay, and then how did they test it? They tested it in various experiments, and their discoveries are, number 1, there's high accuracy in detecting unseen classes. So their novelty detection is actually good. And when we say unseen classes, it's only the 2 unseen classes, the cat and the truck. Okay, so which means their novelty detection technique does not misclassify, or would know, given an image of a cat or an image of a truck, that it is not among the 8 other classifications or classes. So a cat is not misclassified as, let's say, a dog, because it knows, because due to the high accuracy of the novelty detection, it can detect if something is unseen. Okay, so they also discovered, or they also was able to generate high accuracy on seen classes, even if we include, even if there's a novelty detector in the solution, even if we give it distractors like those unseen images, it still knows when something or an image has already been seen. Okay, so the classifier for the seen classes was not compromised, even if it is expecting that some images have never been seen. Okay. Okay, so in your own words, what were their discoveries? So I explained to you the process, and in your own words, do you recall what their discoveries are? So this would be at the latter part. Normally, this would be written in the conclusions they want to come up with. So they want to come up with a solution that can still classify an image, even if that image's category was never part of the training set. That's what they wanted to do. Because in the traditional way, that image will be forced, or the classifier will still assign or misclassify. I will still assign a category from those that it knows. But in this case, the classifier would simply come up with an unseen label. But the label is still within the multimodal embeddings. So what were their discoveries? So Somebody said the model is able to identify images that were not seen before. Okay, so actually, yes, that's true. So they were still able to identify images whose category was never seen in the training set. Okay, if there are no similar categories, it won't recognize the unseen category at all. Actually, this is true. This came out in the result. So since remember what they're doing is finding so from the novelty detector, it will say whether a certain image's category has been seen or not. If it is unseen, what is done to identify the category is simply to compute the distance of that image embedding to the nearest category in the multimodal embedding. So if the category is also not known, it would also not know, come up with that category. Let me just clarify that. That is actually a good point. So these are the categories or these are the expected categories. Okay, but during training, cat images and also truck images were not included, which means the classifier only knows of automobiles, frogs, ship, airplane, horses, birds, dogs, and deer. Okay, but during testing, there are images of cats and trucks included. Okay, as the second person pointed out, given an unknown, given a testing, if something is unseen, so meaning it may fall somewhere here. The computation that is being done to identify whether it's a cat or a truck is to compute the distance. Okay, is to compute the distance from this unseen image embedding to the nearest unknown category. So yes, in the first place, it still knows what the unseen category is, and it is here, the truck and the cat. So let's say, what if we add another image of a tiger? So most likely the tiger is somewhere near the cat, right? But it doesn't know, the mapping of a tiger image embedding was never mapped here. So hopefully it falls somewhere here, but it doesn't know, it wasn't labeled that it is here, that it is a tiger. So most likely the tiger would still be identified as a cat. Okay? So to some extent, there is still knowledge of the unknown categories. Okay, so I highlighted some of for me are the major discoveries from this study. So first, on the multimodal embedding, so on the use of the multimodal embeddings, the semantic word vector representation can help transfer learning between modalities. So in this case, it's the image and the text modality, even when they were learned in an unsupervised way. So take note that when this representation here is word embeddings coming from a corpora. So it was created in an unsupervised way. The only thing here that is supervised is the mapping of the image categories, okay, to the word vectors. And even if the word semantic vector or the semantic word vector was created in an unsupervised way, it still proved to be useful during transfer learning between text and image modes. Okay? And then second, they used a Bayesian framework to capture both zero-shot classification and the scene classification into one network. Okay, so, and it showed from their results that combining both zero-shot and scene classification in one framework increases or improves performance. So that for me is also a good thing, because for me, intuitively, I would separate classifying the unseen from classifying the seen into different separate frameworks. But in their case, they combined it and they called it a Bayesian framework, and they found out that it is useful to combine them. And then a fully unsupervised model, just like in their case, the novelty detector, can tell the difference between zero-shot classes, okay, or classes that were never seen, with a very high level of accuracy, and that is 90%. So these are for me, these are the most important discoveries or conclusions from this work. So let me just expound. When we read the paper, as a teacher, I would tell my students that they have to understand the graphs that are part of that paper, because it would show how they reach or how they came up with their conclusions. And then so in that paper, the two most important results are coming from these two figures. So for the first, wishing images use combinations here, various combinations of zero-shot classes. So what does that mean? So if they did not include the dog images during training, the cat was never included. So aside from the cat images and the truck, if they also did not include dog images, the accuracy is around 50%. So at zero shot of cat and truck without training data from the dog, the accuracy is at 50. So if they did not include airplanes and automobiles in the training set, the accuracy at this high, etc., etc. So if they did not include, in their case, they did not include both the cat and the truck, right? So these two, the choice of these two came up with the highest accuracy at 90. That's why the in their experiments, the unseen classes are cat and truck. Okay, so but aside from these, they actually perform experiments on two other combinations of unseen classes. Okay, and they say that choosing cat and truck are good combinations because the truck can actually be detected via the automobile because it's close to an automobile. Okay, and the cat is similar to some of the animals like the dog. That's why it got the highest accuracy. So from this table, it is actually telling us that, or they are actually telling us that the choice of what are known, the categories that are known, and what is unknown is also very important because the known categories should have, there should be enough information from the known categories so that the model would be able to guess the unseen categories. So let's say the truck, like I said, the truck can be guessed or can be somehow be deduced because there's also the automobile and maybe even the ship. So there's a way to differentiate different types of transport system from the unseen truck. Okay, unlike when we remove the cat and the dog, there might be information from the dog that will help in the identifying a cat. Okay, and then for the second graph, they check the average performance of the classifier, this one, on the seen classes. Okay, so they check the average performance of the classifier if the overall data set includes both seen and unseen images. So they implemented two novelty detectors, the Gaussian model and the loop model. These are the novelty detectors. And these are the detectors that decide with a certain probability or a fraction when the novelty detector says that an image is unseen. Okay, so each image is passed through each of these novelty detector. And if the detector says that's a seen class, okay, The image is then passed to the softmax classifier, so that that classifier will give one of the scene classes. Okay, but if the novelty detector says that this is an unseen class, the image is assigned to the class, as I've said, to the nearest semantic word vector for the unseen category. So it is matched, computed against the cat and the truck categories, and see, check how close is which one. Okay. The image, ito, this part here, this is at 90% accuracy, which is similar also to this part. So what does that say? It's saying that if the novelty detector is told that there will be unseen classes, okay? If the novelty detector is told that there will be unseen classes, okay? So which means, that's why the probability is 0 here, meaning it will see unseen classes. It's 90% accurate that an unseen class would be detected. Okay, that's what it's saying here. Okay, which is cool. Actually, this part is cool. So if the novelty detector is expecting unseen classes all the time, the accuracy is very high. It's at 90%. Okay. However, they also pointed out, yeah. I think they also, is somebody going to say something? Mm-mm. Mm. Mhm. Okay, so I'll just read the message. Sorry, I did see this, Shuruthi. So I have a doubt that how does this system get its label? Unlike supervised learning, here they are using word embeddings too. Can you explain, please? So the unknown label, actually, it's not really unknown. They still know what the unknown label would be, because they know it's either a cat or a truck. There are two unseen labels. So given an image, that image would be converted into an image embedding, which can be mapped to the word embedding here, or the word semantic space. Let's say it falls here, then it is computed. The distance between the other labels would be checked. So the assigned unseen label would be given to the one that is closest to the input image vector. Did I answer the question, Churuthi? Well, it's also possible that a label can be deduced from the word embeddings themselves. So let's say uh, somewhere here, uh, somewhere here, based on the embeddings, we can, a new label can be deduced. So let's say somewhere here, a toad might be mentioned so much, so that this part can be a toad. These images that would fall under this area can be labeled as toad. So that's what single modal embeddings are used. That's how single modal embeddings are used in novelty detection. But what is different from them is, for them is, they used a word space embedding to label an image that is never, whose category was never seen. Can the model also take into account the possibility that it is related to two or more unseen labels? Yes, it depends on where an image's vector would fall in the space, on this space. So it's possible that it's close to two. But remember, they also use novelty detection. So in novelty detection, it would know whether the category has been seen or not. So if it's an unseen label, it won't be compared against the seen labels, these labels here. Okay? I think it is also intentional that the cat and the truck labels are really very far in the space. So the chances of an image that is labeled as unseen to be both a truck and a cat would be low in probability. So just like actually, it's one of the things that they mentioned, the paper mentioned, that the choice of the unseen labels is important. So if they are too close together, if the unseen labels are too similar, it would still be very difficult to classify unseen images properly. That's right. As Lori Lee pointed out. Other questions? Ruthie, did I answer your question?
Yeah, yes, actually. But here comes another doubt. Uh, the label is also right. Maybe the unseen cat can be mapped to uh, the label truck. Is that possible?
Can you repeat that again? Is it possible to map the what?
Possible to map the unseen image of cat to the label truck?
Is it possible to map the unseen image of cat to a truck? Is that it?
Yeah, because
Ah,
the image of truck is also unseen.
okay.
How the image and the word embeddings getting mapped. That's what my doubt is.
Is it possible for an image of a cat to be labeled as a truck? Is that the question?
Yeah, it's
Using the distance formula, since a given image, if it is a cat, the information on that image would be represented already as a vector. So if it is mapped to this space, if it is a cat, it should fall somewhere here. So it's the chances of an image of a cat to be labeled as a truck would be small because the embedding space would prevent it from that happening. So unless in the word word semantic vector, so here in the word semantic space, the cat and the truck are related. That's the only time a cat would be uh, misclassified as a truck. Because even in NLP, even with words, a cat is very different from a truck. So that information alone from the word embeddings would make the cat word embedding very far. It will be not so close to the truck. And since they map the cat category to the of an image, the cat image the cat category was mapped close to the cat information on the word semantic space. I don't think it would be highly likely that cat images would be mapped to trucks because they are not close to each other. Even with the way we understand those two words, they would not fall within close proximity in the word semantic space. Did I answer the question? Actually, I'd like to know what your personal take on the paper is. So I guess some of you might be doubting the efficiency based on how high the results are or the performance of the different components of their solution is. So may I know, for you, what's your personal take on this paper?
Actually, I am departments but also supervising learning. So when I gone through this paper, I
I'm sorry, Sir Ruthie. I really cannot hear it properly. Could you just write it on the Mentimeter? Did I understand it right that there's some doubt on your end? Or the effectiveness of the solution? Actually, because I also have my own doubts on the solution they presented. It's not a doubt, but it's more of, is it really that effective? Everyone could use the Mentimeter to place in your personal take on this paper. Due to time considerations, it's nine. I just saw that it's now 9 o'clock. Here's my personal take. Yeah, here's my personal take. So they actually divulged or declared in the paper that the experiments were on balanced classes. So which makes me wonder, in this case, there's that part where they manually map the image embeddings to the word embeddings. I wonder if that technique would still work when the data is no longer balanced. That's one. If there are more than 10 classes, 10 categories that we are considering. So in their example, they really selected the 2 unseen classes intentionally. Okay, they made different combinations on what would be the perfect unseen classes. But in reality, do we have the time to actually do that? To some extent, they also know what the unseen classes are. That's why it can easily be mapped to the space. So that's the part. Those are the things that I think they needs to be more work on, or more work should be placed on. And actually, when this paper was assigned to me by Ali, I checked. As I've said, there are more than 1,400 citations of this paper, and there are a lot of works that are addressing an imbalanced data set for a similar technique, and also the use of more than just embeddings. In their case, the knowledge was simply on embeddings coming from a text corpora and the training image data. But there were works that considered image knowledge, not just from the training data. So it's a bigger multimodal embedding. And there were also other works that would consider 20 classes with 20 unseen classes on an imbalanced data set. Okay, so though I realized these 3 things when I read the paper last week again. For the past 9 years, there were so many works that were already addressing similar things. And for others, they did it the other way around. They are coming up with an NLP classifier. So it's a document that is being classified, and there are information coming from images that are supplementing the text information. Okay. So I guess I'll end here because it's at 9:03. We're now 9:03. In the interest of time, I'll end here. Ali, back to you.